All right. So let me first give you an idea of what this talk is not going to be like. I decided to give a quirky version of this talk rather than the usual sort of survey and summary. And one reason for that is that I'm actually, if you want the usual survey, I'm not the right person to give that talk anyway because I haven't been directly involved in most of the things I'm going to talk about, and there are many other people here better qualified to give that kind of talk. But also I wanted to get to this other point that, as I understand it, the point of this workshop, and for this audience here, is not to convince you how wonderful the linear collider is, and also not to convince you that lots of other people have done lots of great work already. But rather to convince you that there's lots of interesting things to do now, especially for new people that haven't been so involved in linear collider stuff. So I've tried to give more of an impressionistic view of areas that I think are somewhat underdeveloped or otherwise provide opportunities or what I think are interesting approaches to thinking about linear collider physics. So let me start. Since Dan's here, he'll probably say he's been misquoted, and he probably meant this in some other sense. But I think this is it's a question you can ask seriously. Is what really is the point of linear collider physics studies? And I sat down and tried to think about this in some detail, and this was the list I came up with of what the motivations or goals ought to be of these studies. There's the thing which has been going on for a long time now, which is trying to really sharpen the case for the machine and also figure out how to optimize what the machine parameters ought to be, what the baseline detector design ought to be. That's not going to be the subject of this talk, although it's certainly an important goal. Two other things that I won't get into in this talk, but which are important, are what Sven already mentioned is this point of doing theory calculations to reduce theory uncertainties to the point where they're going to be comparable to what we hope are the LC experimental uncertainties. And also there's presumably more specific sort of detector challenges or enhancements that come up in certain kinds of physics contexts that don't come up, say, maybe in Higgs physics, but do come up, say, in extra dimensions. But I won't get into that either. What I will get into is the question of how physics targets, of course, change as the theory landscape changes, and you may have noticed that the theory landscape changes rather rapidly, and what seemed to be the really cool thing this year may not be the cool thing by the time you build your linear collider. Secondly, I think a very underdeveloped point here is the complementarity of the linear collider, not just with the LHC, which has already been mentioned, but also with everything else that we're doing in physics and even things people are doing in astrophysics. I'll get into that. And then another important thing you do these studies for is to try to discriminate different kinds of new physics, not just say, to what percentage can I do such and such physics, but how do I discriminate different kinds of new physics that might be there. And I'm going to go through that point first. Obviously, there's an infinite number of new physics scenarios that are potentially accessible to linear collider. And even with the famous precision measurements you can do, even with 1% level measurements, it may, and it's easy to show this, it may be very hard to discriminate between different kinds of physics explanations of the same signal. And of course, as you might expect, this is especially true if the new physics is manifested not by actually producing a new particle, but it's manifested through virtual effects from some even higher energy stuff, or through new particles that are hard to see because you see them as missing energy signatures, you don't see them directly. And I wanted to give you a couple examples of that. This is recent work by Jim Wells and collaborators coming out of SNOMAS, where they looked at two questions that have to do with extra dimensions. This is looking at the simplest models of extra dimensions, what are called ADD, large extra dimensions, where there's sort of a classic signature at a E plus E minus collider where you look for a photon plus missing energy. The missing energy is because you made an extra graviton that escaped off into the extra dimensions and took away energy. So one of the things you'd like to know is how do I tell if I'm lucky enough to see a real signal of extra dimensions? What can I tell about the extra dimensions? And the easiest question to ask in this context is how many extra dimensions are there? So that's one thing you'd like to know. And also, you'd like to be able to discriminate extra dimensions from other exotic physics explanations. For example, supersymmetry, as these people point out. You can have a case where you have very light gravitinos, and you have a very similar missing energy signature where what you made was a pair of light gravitinos accompanied by a photon. So how do you discriminate that from extra dimensions? Well, this question of counting dimensions was looked at by Graham Wilson, and there's a very nice discussion of this in the Tesla TDR. And the answer is that the simple way to count dimensions in these simple models is just to run at 2 different energies. So you run, say, at 500 GeV, and then you run at 800 GeV. And with those 2 points, you get very good discrimination, at least for these simple models, to count the number of extra dimensions. Here, delta is the number of extra dimensions. So that's encouraging, because actually we don't expect that the real world of extra dimensions would be as simple as these models. So it's nice that in the simple models, you get such very good discrimination like this by running at different energies. The thing that's new, was pointed out at SNOMAS, was that actually you don't even have to wait for your 800 GeV or 1 TeV upgrade to do this counting. You can run at 2 similar energies, say 475 and 500 GeV, and that already, even though it's not a big energy difference, because you're doing these 1% measurements, gives you discrimination of the number of extra dimensions. And the other thing they looked at was, how do you tell a graviton from a gravitino? Is this extra dimensions, or is it SUSY gravitino production? And there you see this is somewhat challenging. I can't even really point out which curve is which. The lowest curve here is the curve, this is photon energy versus cross-section. The lowest curve is the gravitino, is the SUSY signal. And then the higher curves are various numbers of extra dimensions in the extra dimension case. And you see this is a challenge, but there is some discrimination. And then what they claim, at least at sort of a theorist level analysis, is that, again, you have enough precision at the linear collider that you can tell some of the extra dimension scenarios apart from SUSY. And then there are certain cases, in this case 6 extra dimensions, where actually you can't tell the difference by doing even these precise measurements. So you need some other kind of trick. Here's another SNOMAS study that also gets at this same question of how do you discriminate different kinds of new physics. Here they were quite ambitious. They looked at the case of, here I'm seeing virtual effects. I've got new physics. I'm not actually producing new particles, but I'm picking up virtual effects of things. And those effects I see as contact terms, something that I would describe as contact terms that show up in lepton pair production, E plus, E minus, mu plus, E minus, or taus. And then I'd like to figure out what that was. And they did the exercise of doing this, and they looked at 4 different possible explanations for the same contact terms, coming from lepton compositeness, string excitations, the actual excitations of the fundamental strings of string theory, and then 2 kinds of extra dimension scenarios. And then they asked themselves, could I actually discriminate what was what here? And the answer is you can. And the reason you can basically is, again, you're doing precision measurements. That's always the key. And then the other key here was that you combine information from other channels. So I look at precision measurements with angular distributions, and then I combine these 3 different channels, E plus, E minus, mu plus, E minus, and taus. And then what you get in the end is this curve over here, where the different colors represent the different kinds of physics that I'm trying to fit to here, where here they've taken one of these extra dimension scenarios to be the real model, and then they're looking at how these bad explanations fit to this simulation. And then the peak here is good. The high curves are good. That's a good fit. The low curves are a bad fit. And you see that by the time I've done all these measurements and combined all the channels, the real explanation, in this case extra dimensions, just jumps out at you. And furthermore, you figure out what is the fundamental scale associated with these extra dimensions. So that's the kind of exercise you might actually be doing in with real linear collider data. Now, the second point I wanted to emphasize even more has to do with complementarity between linear collider physics and other kinds of physics that we're doing. We certainly hope and expect that there's going to be lots of glorious new results before the linear collider turns on. And we'd like to understand what is going to be the connection between the linear collider physics program and all this other new physics that we have our hands on. Sven mentioned this very important point of complementarity between the linear collider and the LHC, and the point that there hasn't been enough study of this. And so I certainly want to reemphasize that this LC-LHC complementarity needs to be studied, I think, a lot more. There's a lot of fertile ground still there. But I'm not going to talk about that. I'm going to talk about the relation between the linear collider and flavor physics, Now, we just heard in the last talk that when you run the linear collider in giga-Z mode, of course, there's all kinds of connections to flavor physics, and that's not what I mean. What I mean is the different question of the linear collider is supposed to be our high-energy machine, our window on the new physics at the TeV scale, and then by extrapolation to even higher scales. What is going to be the connection between that physics program and the stuff that we're doing with heavy flavor physics, with neutrino physics, and with rare processes, kaons, and other things? That, I think, is it's a very important question, and it's something that's largely unexplored, and there's lots of room for people to do new things here. Here's an example of something that's new. This is, again, a study by Wells and collaborators from Snowmass, and what they looked at is what's the overlap between the linear collider and looking at lepton flavor violation and the planned experiments at Brookhaven to look at mu-E conversion lepton flavor violation. And again, it's interesting to see that with some parameterization of the new physics that would produce this, that again, you have some regions where you have overlap between what you do with these two kinds of seemingly very different physics programs, and then you have regions where one or the other of them has access, but not both. So that's the kind of thing that you want to think about, how to make these explicit connections, and it largely has not been done. I'm going to get into this. Here's an example of something which I'm pretty sure has not been thought about for the linear collider, probably because it wasn't considered one of the most interesting new physics scenarios. But I think in the past year or so, there's been a sort of increasing interest in this general idea. Here, what I basically am talking about is the notion that there might be at least one pair of 100 GeV, a few hundred GeV-ish exotic vector-like, bottom-like quarks, maybe with top-like partners, maybe with other kinds of partners, maybe by themselves. So I'm just talking about this in the general sense of new heavy vector-like quarks. This is certainly an idea that you can motivate in many ways. You'll hear a talk tomorrow by Carlos Wagner about how actually, if you cook this up in the right way, it's something that might actually be showing up or be explaining quirks in the current data. People have also looked at the case of this. It's very important in a lot of different flavor physics experiments that we're talking about now, because these things could be the source, if you control them, they could be the source of small but interesting flavor-changing neutral current effects, which could show up in kaon experiments, could show up in B factories, could show up in lots of different ways. And so this is an example of a robust set of new physics things that can show up in lots of different flavor experiments, but you would produce them directly at the linear collider, and again, you'd like to understand the relationships between these things. And furthermore, they're increasingly interesting from the theoretical point of view. People have known for a long time that there was a motivation for these coming from guts, and I think John Rosner will probably talk about this tomorrow. In E6 guts, you naturally get extra particles of this type. But more recently, people have realized that when you try to use extra dimensions, the general idea of extra dimensions, to make models of flavor, you also tend to get extra funny light particles of this type, they're basically sort of anomalously light Kaluza-Klein modes in the case of extra dimensions theories. And this is a rather general, new, robust idea for making flavor models. There's different things on the market now. Probably lots of new things will be coming along. And the idea here is basically that flavor has to do with where the different fermions live in the extra dimensions. This plot here, which is from Kaplan and Tate, is just showing different fermion wave functions, sort of showing you where the different fermions of the standard model live in the world of an extra dimension. And furthermore, people are just starting to do this, but if you try to make serious models of flavor in extra dimensions, you make predictions, and the predictions are interesting for things like the linear collider. For example, this is a very recent model which they tried to do some serious things with flavor in extra dimensions, and then they predict that there's a new exotic particle. This one's actually top-like, it's not bottom-like. A pair of these things, vector-like, and they predict the mass to be 400 GeV. And then they predict that there isn't anything else, so that this, if you like, is the signal of extra dimensions. It's not a whole tower of Kaluza-Klein modes, because most of them are inaccessible. The signature of extra dimensions is this new exotic top-like, vector-like pair. So here I think there's going to be a lot of theoretical development on these things, and it's wide open in terms of studying what you would actually do with these things at a linear collider. And this is my joke that, I don't know, if you know this neighborhood, you know that within easy walking distance, there are many commercial establishments that advertise exotic bottom physics. Yeah. How am I doing in time? Okay, so that was heavy flavor. Even less exploited, I think, is the connection between the linear collider physics program and the neutrino program. There are a few connections. In fact, they were the only two that, in my ignorance, I was able to come up with. Clem is here, and he can tell you that if you run the linear collider in E-E- mode, you have the chance of actually having sensitivity directly to heavy Majoran and neutrinos. So that's certainly interesting if you can do it. Another interesting study that has been done, I think Marco Diaz, who's here, was involved in this, is you can look at what's called R-parity violation in supersymmetry. R-parity is the discrete symmetry that tells you that superpartners are produced in pairs, and it gets rid of a bunch of nasty tree-level operators that would violate Baran and lepton number. But you can look at SUSY models in which R-parity is broken in certain ways, and there are rather nice, fairly well-motivated models for doing this, for breaking R-parity, in which you've broken R-parity, and thus what you thought was the stable LSP, the lightest neutralino, actually isn't stable anymore. It decays because of R-parity violation. So that's interesting. But furthermore, it's much more interesting because the decays of the neutralino are now related to parameters of neutrino oscillations. So that's very interesting. And in fact, in the study, that if you end up in a model like that, you can really make a direct experimental connection between neutrino oscillation data that you went out and measured in the neutrino program and branching ratios or ratios of ratios for neutralino decays into various modes. And what this plot is supposed to show you is that it's a very clean relationship that doesn't depend on other supersymmetry parameters. So if you got into a scenario like that, that would be great. You'd have really a beautiful connection between linear collider physics and neutrino physics. But really, I mean, more generally, you know, what we always claim is that the linear collider is one of the reasons it's a great thing is that it's going to be our window to physics at really high scale, like the Gutt scale or the Planck scale maybe. And of course, we also claim that neutrino physics is really interesting because that's sort of a window in a different sense onto very high energy scales. And even if you don't believe in Gutt scales, when you translate this all into the extra dimensions, it's sort of the same thing. They're both neutrinos and linear collider are supposed to be windows on extra dimensions. But then somehow, someday, you're going to have to make a connection between those two things. And you're going to have to say how all that neutrino data is related via the high energy scale stuff to stuff that you measure with precision at linear colliders. And really, people have not grappled with this at all, I don't think. It's really it's a big, wide open field to think about. And just to give you a taste of how things could get really interesting and also to plug my own paper, you know, the neutrino sector is already weird, and it could get even weirder. We have a paper out where we say that the obvious explanation of all existing neutrino data is that there's CPT violation in the neutrino sector. Well, you know, maybe that's not true, but if it is true, you can prove it with the experiments that are coming online. And if we know that there's CPT violation in neutrinos, then that's going to be a big agenda item for the linear collider. It's going to really dominate our speculation about theory for a long time to come. So it's not just that you want to connect to neutrino physics. Things may happen in neutrino physics that really change your whole theoretical perspective for what's interesting. The last motivation I'll talk about was just this general notion that theoretical ideas change, new ideas come along. If you've been paying attention the last 4 years, you've seen all kinds of crazy things on the market. In addition to these ADD large extra dimensions, there's lots of other kinds of extra dimensions around now with very different kinds of phenomenology. I'll mention the first one in more detail. There's new stuff happening in supersymmetry. There's other weird things. They're sort of inspired by string theory, like non-commutative gauge theories. So there's all kinds of stuff coming up, and this stuff has different kinds of consequences for the linear collider. So for example, let me contrast for you Randall Sundrum, which is a kind of extra dimensions scenario, with the ADD extra dimensions that I was talking about before, where you go out and look for these missing energy signatures with gamma plus missing energy. This has a very different kind of phenomenology. It is also an extra dimensions model. It's a model in which there's a fifth dimension. There's brains, as there are in ADD models. We live on a brain, as in these other models. But there are differences, and I won't have time to get into them, but those differences, at the end of the day, they give you a very different phenomenology, because what happens is you get, instead of an ADD where you get a bunch of copies of the ordinary graviton very closely spaced and massed and gravitationally coupled the way the usual graviton is, here what you get are heavy gravitons which don't couple with gravitational strength. They couple with suppressed, but only TeV suppressed strength. And so those are things you can actually produce as resonances. You can produce them, and then they can go back into standard model stuff, and you can see them as resonances either at the LHC or at a linear collider. Resonances of some spin-2 object, which couples in a flavor universal way. That's going to be your heavy Kaluza-Klein gravitons. So this is a study by Human and Joanne and Tom, who are, two of them at least are here, and showing that you can really do a beautiful job on this Randall-Sundrum type phenomenology at either the LHC or a linear collider. And furthermore, they've gone beyond this, and in a scenario like this, where it turns out the world has extra dimensions and you can produce Kaluza-Klein gravitons, you can actually get in scenarios where you produce not just a few Kaluza-Klein gravitons, but on the order of 10 to the 7 of these things per year at linear collider luminosities. So if you can actually do that, you can not only ask, how do I discover extra dimensions and how do I do the simple things like count the number of extra dimensions, but you can start to do what you could describe as precision quantum gravity. For example, you can measure the self-coupling of the 5-dimensional graviton to itself by looking at the decay of one of these Kaluza-Klein graviton modes into a pair of other ones. So you're actually measuring gravity-gravity couplings. And furthermore, I won't get into this, but they show you can do other more detailed things. You can actually try to, in a real way, relate the flavor structure that we see in the real world through the details of the geometry of extra dimensions that you can measure now at your graviton factory. So it's not so crazy to imagine, you having discovered extra dimensions, certainly, that you could get into a scenario like this where the linear collider is really doing something very different from what you originally had in mind. In the last couple minutes, I'll give you another example of something that's new. This is something that's so new that the phenomenology for anything hasn't really been worked out yet to any extent. And it's, again, something where you will certainly see new things happening in the next few years. And, of course, again, there's lots of opportunity to look at this in different contexts. This is the idea of deconstruction. There's many ways to describe this. This is, in a sense, going back to the idea, which I guess started with Technicolor, that with gauge theories you can do anything. And in particular, what these people show is that with gauge theories you can actually mock up the same degrees of freedom that you might have thought were extra dimensions, were the Kaluza-Klein modes of extra dimensions. And in fact, if you're mocking them up sufficiently well, they are extra dimensions, because that's what extra dimensions are. They're a certain pattern of degrees of freedom that you can call Kaluza-Klein modes, and thus represent excitations of extra dimensions. But if you can produce them from a gauge theory in some energy regime, then that's sort of an effective extra dimension. And they show that really in a much very general class of gauge theories that you can do this. You can have a 4-dimensional gauge theory at low energies, effectively a 5-dimensional theory at some intermediate energy scale, and then back to a 4-dimensional gauge theory at very high energy scales. So this, especially the way I've described it, it really sounds like something even more general than extra dimensions, in the sense that it's, first of all, it sounds more dynamical. You're not just postulating extra dimensions, you're producing them dynamically. And furthermore, it's sort of more general, because for every one of these models that seems to mock up extra dimensions, there's a slightly different model in which it doesn't look like extra dimensions at all, but it's certainly related to what you were calling the extra dimensions model. So it's, in a sense, a much more general approach to making models of new physics and really using a kind of funny set of new ideas. So what's the phenomenology of that? Well, nobody really has looked at this. The only thing I can even say, and this is even more this than the rest of this talk, is one of the things that they noticed in these sorts of models is that you can get light Higgs bosons really that stay light without invoking supersymmetry. And part of the way they do that is essentially that the standard model Higgs begins its life in the adjoint representation of some gauge group. And again, this is just an example. There's many ways of doing this, but the idea would be that what we call the Higgs doublet secretly started its life, say, in an adjoint representation of some SU3 group, and which got broken up through some process. And so all I'm pointing out here is that here's a dramatic phenomenological feature of these kinds of models. It seems to be related in a more or less generic way to this feature that the Higgs starts its life as an adjoint. And because of that, it would seem that in these kinds of models, you tend to get extended Higgs sectors where there's extra junk coming along, extra scalar stuff that's coming along with the ordinary Higgs. Now, that's really the extent to which this has been worked out, as far as I know. But it certainly provides us with a new motivation for looking at extended Higgs sectors that are beyond what you do in the MSSM and beyond what you do even in the next two minimal MSSM, and which are motivated by some very concrete set of theoretical scenarios. And that phenomenology, again, may really change your whole outlook for how Higgs physics works. Before deconstruction even came along, people had looked at what happens if you have extended Higgs sectors with weird properties, like, for example, there's a very light CP-odd scalar, what I'm calling A here, much lighter than the standard model Higgs. Well, what happens is it can really change the phenomenology for what you were calling the standard model Higgs, the light CP-even guy. So I don't really know what is the phenomenology of deconstruction, but I know it's interesting, and this, I think, is sufficient motivation to say that certainly in the next few years we're going to see lots of interesting claims from theorists about what is the phenomenology of this class of models. And again, it may be very relevant for what you do at a linear collider. So that's basically all I want to say. There was more, I guess, I could have said about Higgs stuff. One thing also that I think hasn't been mentioned is that for example, in extra dimensions models, a very general property of extra dimensions models is that they have extra scalar fields called radions, whose vacuum expectation values basically measure the size and shape of the extra dimensions. So that, again, is a very general sort of feature of having a world with extra dimensions. And those are extra scalar fields, and it's not surprising to learn that those can mix with the Higgs. And again, that can end up changing your Higgs phenomenology, not necessarily in a dramatic way, but in small ways. And again, the precision measurements you can do with the Higgs at the linear collider would then be the key to maybe unraveling the radion component of the ordinary Higgs. And of course, since that radion is actually measuring the shape of extra dimensions, the ability to extract that information in a linear collider would be of an enormous importance if that's the scenario we're in. So you can have more and more examples of these things, but I hope I've left you with the impression that certainly within the realm of beyond the standard model physics, there is lots and lots of things to do, lots of underexploited and new approaches to looking at things in the context of the linear collider. And there's an amazing amount of stuff to play with and have fun with. So that's my conclusion.
This is an extra dimensions related question, Mike. My understanding is that the Schwarzschild radius is a function of the number of dimensions of a certain size changes. If you could have the number of extra dimensions do something strange, can we make little black holes that Hawking radiate away their energy?
Yes. In these extra dimension scenarios, one of the generic features of them is that it is easier to make black holes. Whether it is easy enough that you can make them at a linear collider is, I think, a little dubious. I think it's a little easier at the LHC because it's probing to effectively to higher energies. So I think a more fair statement would be this. I think two things one can seriously contemplate is, first of all, little mini black holes, by the time they get to the point we can actually describe them the way Hawking describes them, they may be mini black holes, but they're in some sense big. They're thermodynamic objects that have lots of degrees of freedom. Where do those things really come from microscopically? Well, they presumably start out as some kind of stringy thing, because we think string is the theory of quantum gravity. So really what you would see first at a collider is not the black hole, not something you would call a black hole, but you'd see some sort of stringy thing, which at even higher energies would become things that would look like black holes. Second point is that if we actually understood quantum gravity, we could talk about virtual effects of black holes. And I think it is is certainly possible that virtual effects of black holes could show up in linear collider physics. They might be showing up now in physics, and we just don't recognize them because we don't understand quantum gravity.
Any other questions for Joe? Okay, well then I guess it's time to move on to detectors.